Half a gram. That is the average amount of gold inside 1 ton of Boddington's reserve ore. You could hide it under a fingernail. Yet its 2026 technical plan forecasts 38 million tons of ore through the plant in 1 year, roughly 100,000 tons every day. At that scale, losing just 1 percentage point of gold recovery across a year could leave roughly 7,000 ounces behind. That is the impossible equation at the heart of this mine. Recover a microscopic prize without losing control of a machine visible from space. 130 kilometers southeast of Perth, 2 open pits cut into the Saddleback Greenstone Belt, feeding one of Australia's largest gold-producing operations. But scale is only half the story. Most of the resource is hard diorite and andesite. Early test work measured compressive strengths around 150 to 200 megapascals. And the gold is not sitting there as bright yellow nuggets. Its median particle size was measured at just 11 microns. That is smaller than the width of a human hair. To make the equation work, Boddington must move immense quantities of material, expose microscopic minerals, and separate gold and copper from everything else, with no weak link in between. The mine is not one giant machine. It is a chain, and every link begins with an explosion. The first crusher at Boddington is not made of steel. It is the blast. Drill rigs create a pattern of holes across a bench. Explosives are sequenced so the rock fractures and moves in a planned direction, producing fragments the shovels can dig and the crushers can accept. Too coarse and the plant pays for it later. Shovels struggle, trucks wait, crushers choke. Every downstream machine spends more energy reducing fragments that should have been smaller from the start. This is why Boddington's ramp-up was treated as a mine-to-mill problem. Engineers measured rock strength, audited blast patterns, and tracked parcels of ore through stockpiles and crushers. They could connect a specific blast with the way the plant behaviors hours later. Instead of asking whether one machine worked, they could ask the question that actually mattered. Did the entire chain recover more metal for less energy and cost? At the pit, autonomous haul trucks now repeat the transport cycle. Newmont's current reporting lists 41 production autonomous trucks, and Boddington became the first gold mine to implement a full autonomous haulage system in 2021. People still define routes, maintain the machines, and supervise the system. Automation cannot rescue poor fragmentation or a blocked plant. The trucks deliver ore to 2 primary gyratory crushers. But even after the blast and 2 crushing stages, Boddington still faced a problem capable of following every ton through the mine. This rock did not want to break. Boddington could have followed the conventional route. Send partially crushed ore into a semi-autogenous grinding mill, where rocks and steel grind against one another. But tests exposed a costly problem. Before the modern mine opened, engineers ran more than 100 laboratory tests, 4 SAG mill pilot campaigns, and 3 high-pressure grinding roll trials. The ore strongly resisted breakage. A conventional circuit was expected to demand roughly 30% more power than normal calculations suggested. At Boddington's scale, 30% extra power would become a permanent tax on every ton processed. So the design placed high-pressure grinding rolls at the center of the circuit. An HPGR is not a pair of giant teeth chewing individual boulders. 2 counter-rotating rolls draw in a packed bed of smaller particles. Hydraulic force squeezes that bed at extreme pressure. The particles crush one another, creating fine material and microscopic cracks that make the next stage easier. Boddington has 4 of these machines. Each is rated at 6.5 megawatts, and together the current technical report gives the circuit a nominal capacity of 8,000 tons per hour. This is where the simple story, engineers installed a magic crusher and saved the mine, falls apart. The HPGRs were selected through extensive testing before construction. The later engineering work was optimization, better blasts, revised crusher settings, and simulations linking the mine to the mill. The rolls solved one bottleneck. They did not produce recoverable gold. The particles leaving them were smaller and more fractured, but the gold was still trapped. To expose particles only microns across, Boddington needs 4 enormous rotating drums. Beyond the high-pressure rolls, the scale rises again. 4 ball mills performed the final assault on the rock. Each is roughly 8 meters in diameter and 13 meters long. Each has a motor rated at about 15.6 megawatts. Together, their installed drive power exceeds 60 megawatts. Inside each drum, steel balls tumble through a slurry of crushed ore and water. Impact breaks particles, abrasion wears their edges away. Cyclones separate material fine enough to advance from material that must return for another pass. Gold and copper minerals are physically bound to waste rock. Until those grains are exposed, chemistry cannot reliably reach them and flotation cannot reliably separate them. Grind too coarsely and valuable metal leaves with the waste. Grind unnecessarily fine and the plant burns more power while creating particles that are harder to handle. The target is not as small as possible. It is the size that unlocks the most value. That target changes with the ore. Operators watch power draw, particle size and throughput, trading one constraint against another. Even after all that power, the plant has not produced a bar of gold. It has produced a slurry, water carrying a cloud of finely ground minerals. The first half of the plant separates by size and strength. Now it separates by surface chemistry. Now the ore reaches a fork in the story. Boddington contains both copper and gold, so the plant needs two recovery paths. In the flotation circuit, reagents change how selected particles behave in water. Air is introduced. Valuable copper-bearing particles attach to bubbles and rise into a mineral-rich froth. That froth becomes a copper-gold concentrate. But flotation is not perfect. If the plant stopped there, gold would remain in the material that did not float. So the flow sheet divides into two recovery paths. One path captures concentrate. The other treats selected flotation tails through carbon-in-leach tanks. Cyanide, in a controlled process, dissolves accessible gold. Activated carbon captures it from solution. Later stages recover that gold into doré bars. The plant is matching different extraction methods to different forms of the same ore. Regrinding, oxygen, pH, and time all shape the result. Newmont's current life of mine model assumes average recoveries around 85% for gold and 81% for copper. Those are planning values, not a promise for every parcel. When the head grade is only fractions of a gram per tonne, 1 percentage point matters. At 38 million tonnes a year, tiny changes in recovery can represent significant amounts of metal. The control room is hunting losses too small to see directly. This is the true product of the control room: precision at scale. And every tonne entering the plant creates another output that must be managed after the valuable fraction is removed. Gold leaves Boddington by the bar and in concentrate. But for every tiny valuable fraction recovered, almost all the original rock remains, and that creates the mine's next bottleneck. After processing, finely ground tailings and water move to storage. The active F1-F3 facility has a proved capacity of 750 million tonnes. That is authorized capacity, not the amount currently stored, but it shows the reverse scale of mining. The gold fits inside a secure room. The remaining material requires engineered embankments, water management, and decades of planning. The current technical report says the facility operates as zero discharge, with water returned to the plant for reuse. Instruments monitor water pressure and movement against trigger action plans. Storage capacity is therefore production capacity. Newmont's plan assumes an expansion and later an additional facility, both dependent on engineering and approvals. If storage is unavailable, the processing chain stops, no matter how well the crushers are running. The mine is also a major electricity consumer. 4 ball mills alone have more than 60 megawatts of installed motor power, before crushers, pumps, and conveyors are counted. Newmont has signed a renewable power agreement with Colgar Wind Farm commencing in 2026. The company says it is expected to reduce Boddington's site emissions by up to 70% over time. Changing the electricity source of a plant built around crushing and grinding can change emissions at comparable scale. So which machine makes Boddington possible? The autonomous trucks? The high-pressure rolls? The 60 megawatts of ball mills? None of them alone. Boddington's most impressive engineering is not any single object. It is the connection between them. The geology informs the blast. The blast controls fragmentation. Fragmentation changes crusher performance. The rolls create cracks that help the mills. The mills determine liberation. Liberation determines recovery. Water and tailings capacity decide whether the journey can continue tomorrow. That is why engineers tracked ore from individual blasts into the plant, measured rock strength, tested scenarios, and changed operating practices. The objective was not to make one machine look efficient. It was to improve the whole chain. It is also why the popular story of a mine suddenly saved by one crushing technology is so tempting and so incomplete. High-pressure grinding was a crucial design choice. Autonomous haulage is a striking achievement. Flotation and carbon-in-leach are sophisticated recovery systems, but none works alone. The mine survives on coordination. To recover a tiny amount of metal, Boddington must control an enormous amount of rock. A ton enters with barely more than half a gram of gold on average. It is blasted, hauled, crushed, compressed, ground, floated, and leached. Its water is recovered. Its waste is stored. Then another ton arrives behind it, and another. Nearly 100,000 times a day. The gold may be microscopic. The system built to find it is anything but.